Hi zkSummit, I'm Igor Gulamov from ZeroPool, and we are building privacy engine for blockchain supporting smart contracts like Ethereum, Near, Polkadot and Waves. One of problem are going to solve when we building our solution is that if we use UTXO based private transactions, we need to publish for each input UTXO a nullifier. In case if nullifiers are not collision resistant, we need to spend 10 bytes per each nullifier, and this data is expensive in terms of gas and storage. Else, if we are going to use collision resistant nullifiers, we need to spend twice more space, and collision resistance is important if we don't want to check our nullifiers on collisions, because collisions are losing money. So if our nullifier is already present, we cannot spend these assets. This is how account-based privacy works. We have one account in the input and one account in output. And we need to publish nullifier only for input account. We merge all data, all amounts from input UTXOs into this account, and we create some new UTXOs in output. Our input UTXOs will be considered to spend because we have spend interval field in our account structure, and we increment this interval, and all UTXOs belong to account owner considered to be spent if these UTXOs are inside this interval. So how it works? We just publish out commitments into our Merkle tree, and when we spend some UTXO, we update our account and increase the right border of interval, and all UTXOs inside the interval considered to be spent. It's important that it's enough to publish on-chain only output commitments, not separate account hashes and UTXO hashes, because if receiver knows only hashes of his data, he can build Merkle proofs and perform new transactions. So encrypted UTXOs and accounts could be moved to not so expensive storage like historic nodes and similar solutions. This is a scheme of our circuit. So we have UTXO structure with 3 files, and account structure. We have interval here. In the most simplest case, this is interval from 0 to the value. In more complex case, we can work with a set of these primitive intervals. This approach allows to make our user experience better. Delta amount is parameter used for withdrawals and deposits and gas fees, and this is output UTXOs and UTXO hashes and account hashes. This isn't public fields of our zkSnark, but we can compute hash of all output structure. This is output commitment of our transaction. It is public. So this is how it's working. So this is root of all UTXOs and accounts. This is output commitment. Also, this is nullifier. We have only one nullifier because we have only one account on the input. Also, we perform some check that sum of inputs equals to sum of outputs. So with this approach, we are going to use much lesser storage and data per our transaction than in our deployed to Ethereum beta version. Thank you for your attention. You can check more about our project or on these links. So that's all.
Cool. All right. I still don't see any questions in the chat, so I am going to encourage anyone who's watching to add some, if you could. I think it would be great. But I do have a question as well for Igor. Why did you choose to do optimistic rollup? Why did you choose to use that?
Okay. Our solution was deployed on Ethereum in March 2020. It is very early experiment in private transactions for Ethereum. So that's why we choose existing technology, optimistic rollup, and use it in our prototype.
Cool. And you mentioned that you're building on Near and Polkadot as well. Why are you working with those projects?
Because we love Rust, and most of our source code is built with Rust. We built smart contracts, client WASM models, and zkSummit6 in Rust, including our self-developed library to build circuits, folk script for zkSummit6.
Cool.